So today I'm going to be making a video on the number e. E is commonly known as Euler's number. You might have heard of the number pi, right? Which is 3.14 and something, and it goes on. It's an irrational number. Similarly, there is another number e, which is discovered by Euler, a mathematician, and this number is, I think, the most important number in maths. And basically, just to write the spelling, this is known as Euler's constant. And why is this number important? We're going to discuss soon, but let's try to see what what the number is. Now E is basically 2.7182881828, and it will continue like this. This is an irrational number, which means this will never follow a singular pattern. This would go on and on and on forever, just like pi goes on and on, right? Now, just to illustrate this number, let's forget about this number. Let's try to focus on a particular example. Let's say you have a friend, all right? Let's say you have a friend who has a bank, and as she or he is your good friend, he agreed that he would give you 100% interest. Now, let's say you are a poor boy. You only have $1 with you, all right? You just have $1 with yourself. So you went to your friend and you said, hey, can I get 100% interest from your bank as you were my childhood friend? So he agreed and he said, all right, I would be giving you 100% interest. So let's say you had $1 with yourself, so your principal amount would be $1, and the interest rate is 100%, which is 1. We can say, instead of writing interest rate as 100%, we could also say this is 1 in fractional form, right? So the rate R is 1. Now, after 1 year, if he calculates the total amount that he will be paying you, all right, so the total amount will be given by this formula, P1 plus R to the power n. This is the total amount in your bank after 1 year for 100% compound interest. So this formula would be giving you this result. So let's say you invested $100, and after 1 year you found out that your total amount was 1 into 1 plus 1 to the power 1, because after 1 year we want to calculate the total amount in the bank. So this would come out to be, this is simply 2, right? So after 1 year you would have $2 in your bank. Now, one thing he realized, that instead of calculating the interest after 1 year, he told his friend that maybe you can do something. You can calculate this 100% interest in 2 intervals. Let's say you have 1 year from first month till the last month, right? So this 1 month can be divided into 2 parts, all right? So you can divide it into many parts, but let's start with 2 parts only. So let's say this 1 month is divided into 2 parts, all right? So 2 parts is basically 6 months. So what he did, he told his friend that you were supposed to give me 100% interest. Now let's divide this 100% into 2 parts, which is 50% and 50%. So we divided this 100% into 2 parts, 50 and 50. Now he told his friend that you told your friend that maybe calculate the $1 interest, the 50% interest on $1 after 6 months. So what he did was he calculated. So now 50% would imply that the ratio is 50 divided by 100, which is half, 1 by 2. So now we could say that the formula would be P into, or 1 plus R to the power n, if this is the general formula after 1 year. So now the formula would change to 1 times 1 plus half, right? So instead of 100%, it would be half. Instead of 1, it is halved. But the thing is that we are going to be calculating this interest on $1 after 6 months, but after the next 6 months, on this whole amount we would be calculating another 50%. We would be calculating another 50%. So it would be again 1 by half. So this would be simplified to 1 into 1 plus half to the power 2, right? So you can say that I'm calculating the same 100% interest, but I have divided the interval into two parts. So he calculated the result and he found out that this is, and he gets $2.25 after 1 year. So previously, when he compounded the interest after 1 year, exactly after 1 year, that means he calculated his interest exactly after 1 year ended, he got a total of $2. But when he divided the 100% interest into two parts, and after 6 months he calculated the interest, and then that amount had been put another 50% interest at the end of the year. So total he got $2.25. Now he realized that he was gaining more when his friend was compounding the interest more and more, right? So next he told his friend that, hey, can you now compound this 3 times? So instead of compounding 2 times, he compounded it 3 times. So then the formula would be following the similar pattern. So it would be 1 into 1 plus 1 by 3 to the power 3, because now we have divided into 3 parts, and also we would be compounding 3 times, so to the power 3. So this would come out and give us 2.37. He realized he had gained a lot. Initially he had earned 2, but then he had earned 2.25, but now he is earning 2.37. So he figured out that he could ask more and more, and he could become basically he could become very rich doing this. But let's see what happens when he starts compounding more and more. So now he told his friend that now you compound 4 times. So 1 into 1 plus 1 by 4 to the power 4. And after compounding it 4 times, basically we are dividing the 100% into 4 parts and calculating the interest 4 times in 1 year. So the result would give me 2.44. Now he did this a lot. So now instead of doing it 4 times, he did it 100 times. So now the formula would be 1 plus 1 by 100 to the power 100, which is equals to 2.704. So he had gained a lot. From just $2, he had gained to $2.704. Now instead of doing it 100, let's do it 1,000 times. So 1 plus 1 by 1,000 to the power 1,000, and we are getting the result as 2.7169. Let's do it more. Let's now do it 10,000 times. So it would be 1 into 1 plus 1 by 10,000 to the power 10,000, and it comes around 2.718. So wait, we're seeing something weird here. Initially this $2 rose rapidly to 2.37, as you can see, and then it went to 2.44, then it went to 2.7, but later on you had increased 100 by 10 times more, but the value didn't increase much. It was only 2.7169, and you increased it 10 times more, but still the value didn't increase much. It is still 2.71, and this is also 2.71. So he realized that there is a limitation. He couldn't become so rich if he became more greedy and greedy. Like, he couldn't ask his friend to compound 1,000,000,000 times, and even if his friend did that, he wouldn't earn much, because the compound interest is trying to converge towards a specific value, as we can see. So what we had expected was, we expected that the investment would jump from 2 to a large value, but what we are seeing is that it is jumping a small amount at the initial stage. So from 2 it went to 2. Let's say it went to 2.2, then it went to 2.3, then it went to 2.4, but then it started to flatten out, and it has reached somewhat a constant value. It is trying to reach to 2.718 and something. So if you do this calculation with a larger value, let's say instead of doing it with 10,000, if you did it with let's say you did it with 1 into 1 plus 1 by, let's say, a lot a lot of zeros. Let me just put there 6 zeros, right? I just put here 6 zeros. So again, you put the power as 6 zeros. So if you calculate this thing, this would also give you something like 2.718 and something, right? And you would realize that if you increase this value large, if you make this value larger and larger, at the end of the day you are starting to go towards this value that we had just discovered, that we had just been introduced at the first, Euler's constant. So this E is 2.71828, and the number we had just started to approach towards was also 2.718 and something. So you could so the idea was something like this. What if instead of writing large numbers, what if I write 1 into 1 plus 1 by n to the power n, and let's make n very large. Let's make n larger and larger. So here we can again use the concept of limit. We can say that let us take that n approaches towards infinity. We are going to obviously take a limit, so we have to write limit over here. So we are saying that when n becomes approximately equals to infinity, or basically when we are saying that when reaches towards infinity, what does this number, or what does this expression try to go towards? Where does this number try to approach? And we can see that this number is trying to approach at 2.718281828, and this number is continuous. It would go on and on, and this number is given the special name of E. So we could say that E can be defined by this equation, or we can simply say that limit as n tends to infinity, 1 plus 1 by n to the power n would be equals to the Euler's constant E. Alright, now this is the interesting thing about E. And the interesting part is that this E number appears a lot in nature, starting from waves, quantum mechanics, to even exponential growth, how the population growth occurs. So there are a lot of things where this number E comes from. That's why it's also sometimes used in logarithms, and it's called natural logarithm, where you have a base E, because E is a special number that has a lot of significance in our surroundings, in nature, and that's why it's important to study. And also there's another cool thing about E, that is, if you make E if you try to make a function of E, for example, if we try to do something like this, if we try to say that let a function f of x be e to the power x, then you would also realize that if you differentiate E with respect to x, you would get the same value. Now this is also interesting. There are a lot of ways to prove this. All right, so I have already discussed in my other videos that how to come around with this differentiation formulas. For example, we have learned that the definition of a derivative is given by this expression, f of x plus h minus f of x divided by h. So here, if you consider f of x as e to the power x, you can easily come across this form. You can easily derive this, that differentiating e to the power x gives you a result of e to the power x. So if I just, in shorthand notation, if I just show you this, so you would realize that e to the power x is equals to f of x, then f of x plus h would be e to the power x plus h. So if we put this thing in this formula, all right, if we put this thing in this formula, we will find that e to the power x plus h minus e to the power x divided by h, and we are going to take the limit as h tends to 0, and this should give us the answer e to the power x. This would give us the answer e to the power x. Now if you don't believe me, you can expand it, or I can just show you how you can expand this. So let's take e to the power x common. So let's just break this down from the first. Let's say e to the power x times e to the power h. We have just broken down the indices using the indices rule. So there's a rule of a to the power n plus a to the power n multiplied by a to the power m, and the result should be a to the power n plus m. So here we have two numbers added, so we can break them down like this. And there's e to the power x over here, so you can write h. And from here, what you can do is you can take e to the power x common. You can take e to the power x common, and you can write e to the power h minus 1 divided by h. Alright, and there is a limit sign over here, limit as h tends to 0. And the important part is that you have to know another thing to prove this, which is a different limit. For example, you can break this down. You can say that e to the power x times e to the power h minus 1 divided by h, and obviously you have the limit over here. But the idea is that this e to the power x does not contain the h expression, so we can simply remove the limit from here. We don't need to put any limit over here because this e to the power x does not contain the h expression. So we can say that e to the power x times limit as h tends to 0 e to the power h minus 1 divided by h. And if you research a bit on this limit, this is another limit which can be proved using another lengthy process, and this limit basically evaluates to 1. And I would say you don't need to find this limit, but you can. It's obviously up to you, but there's an easy way to understand what the value of this expression is going to be. So what you can do is you can take h is equals to 0.00001, and this is approximately equals to 0. So if you plug this in the calculator, and you have to put this exact value in e to the power h minus 1 divided by this exact value, so you would get that this expression is approximately equals to 1. You would realize that this, whenever you put this thing in this expression, the result would be 1. So then you can say that the final answer is e to the power x times 1, and this is the derivative proof of e to the power x. So we started off that d dx of e to the power x, and we have reached that it is e to the power x. We have arrived at the conclusion that whenever you differentiate e to the power x, you would get e to the power x. And this same thing, instead of using the first principles of derivative, you can prove this thing in another different way. And to make us, I would try to make a separate video on that, because that's a different thing. Basically what that approach would require is that the expansion we did over here, the expansion we could do over here, this part, we could expand this part using the binomial formula, and you would reach into a converging series. All right, and you could have even reversed that process, and you could have arrived at e to the power x using f of x. So let me just try to explain you in short what I mean. So let's say we are mathematicians and we are trying to figure out two functions. One function is f of x, and the other function is the derivative of f of x. So it is f prime of x. Now we want to find the function so that this f of x and this f prime of x are equal. All right, so let's start with f of x. Let's start with x equals to 1. Let's say that our function starts with 1. So as we said that f of x must be equals to f prime of x. F prime of x simply means it means that dy by dx of f of x. This is just another notation to write dy by dx. So if f of x is equals to 1, then I can say that f prime of x must also be equals to 1, because we are saying that this and this should be equal, right? So we had just equated this. We had said that f of x equals to 1, and for this condition we are also saying that f prime of x also has to be 1. But as you can see that if I differentiate this, I would not get 1, right? I would get 0. So for example, what I'm trying to say is that if I differentiated this function, I would not get 1. I would be getting 0. So I need a 1, because otherwise this condition won't be true. So I could write something like this. I could say that I'm gonna add an x, because if I add an x over here, if you evaluate this, it is gonna be 0 plus 1, which is this. But again, you can understand that the top and the bottom are not equal. So f of x and f prime of x are not equal. So to make these things equal, I need to again add x. But again, if you differentiate this, you're not gonna get back this. So you have to continue doing this forever and ever. So you would get a series like this. You would write like this, x squared, so that if you differentiate this, you're gonna get 2x, but you need x. So you're gonna again divide it by 2. And as you have added this here, and the f of x and f prime of x has to be equal, so you're also gonna add over here. And basically this is gonna continue forever, because this is gonna be a converging series, and the series will be following a pattern like this. All right, 3 times 2 plus x to the power 3 times 3 times 2, then you have x to the power 4 divided by 4 into 3 into 2 into 1. You can write it like this, which is basically 4 factorial. So instead of writing 4 into 3 into 2 into 1, or 3 into 2 into 1, or 2 into 1, I could write as factorials, right? I could simply say that it is x to the power 4 divided by 4 factorial, and 4 factorial means 4 into 3 into 2 into 1. So this whole thing that I was just explaining as a series, you could simplify this, and reach at a valid conclusion. You could say that then my function would have to be 1 plus x by 1 factorial, which is 1, plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, plus x to the power 4 divided by 4 factorial. And this would continue forever. So you're gonna write x to the power 5 divided by 5 factorial, and it's gonna continue till x to the power n divided by n factorial. And this whole series that we have just written over here, if you, let's say, plug f of 1, so you're gonna put 1 in every places where x appears, so you're going to write it as 1 plus 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 factorial plus 1 by 5 factorial, plus it's going to continue forever till 1 by n factorial, right? So if you try to calculate this for a significant number of terms, you would realize that this expression is also approaching towards 2.718 and the number that we have just discussed about e. So this expression, if you say that the number of terms are going to be infinity, if I say that n approaches to infinity, then this whole expression can be said that this is equivalent to the number e. All right. And why is this happening? Why is it trying to converge towards a number? Because we are adding infinite terms, right? So you might think that why isn't it infinity? Because we are adding infinite terms. The idea is something like this, that the denominator is rapidly shooting up. So 2 factorial is basically 2, 3 factorial is 6, 4 factorial is 4 into 3 into 2, which is 24. Then you can calculate 5 factorial, which would be 120. And as you can see, the denominator is increasing rapidly. So, and the numerator is staying 1. So as denominator increases and the numerator remains the same, the whole fraction becomes smaller and smaller and smaller. So overall, there's going to be a converging series. The whole expression or whole series is going to try to converge towards a specific value, and that value is e. So we had just looked up at 2 different ways in which we can prove that the derivative of e to the power x is in fact e to the power x. So this is for today, and if you want more videos like this, please comment down below and I would be glad to help you guys out.